All right, let's peel back the layers on the technology you use every single day. We're going to go from the very, very bottom all the way up to answer this huge question. How do these magical glowing rectangles we carry around actually think? Okay, let's dive right in. So I'll start with a question that sounds like a riddle, but it's the absolute truth of modern computing. The answer? It's silicon. Yeah, that simple element you find in sand is the bedrock of our entire digital world. Our journey today begins by figuring out how we turn that sand into, well, sense. Everything, and I mean everything, that happens inside your computer, whether it's sending an email or playing a crazy demanding game, it all boils down to one incredibly simple little component, the ultimate switch. And here it is. It's called a transistor. And really, that's all it is. It's just a tiny microscopic gate that electricity can either pass through or not. We call the on state a 1 and the off state a 0. This super simple two-state system, that's the entire alphabet for computers. It's literally the atom of computation. Now, a single one of these switches, it's not very powerful by itself. But here's the thing. Your phone, your laptop, they don't have just one. They have billions, billions of them, all crammed onto a chip that's about the size of your fingernail. That kind of mind-boggling density is where the real magic really starts to happen. So the big question is, how do you get a bunch of simple on or off switches to actually make a decision? Well, you teach them to work together. This is the first step in building from simple switches into something that has complex logic. What we do is we arrange just a few transistors together into a very specific pattern, and this little team becomes what we call a logic gate. Each type of gate is designed to answer a really simple logical question, like, hey, are both of my inputs on? Or maybe, is at least one of my inputs on? So take the AND gate, for instance. A great way to think about it is like a really strict bouncer at a club. It's got two inputs, we'll call them A and B. Now this bouncer will only let a signal through that's an output of 1 if and only if input A and input B are both 1. If either one is off, nope, the output is 0. No exceptions. And this is where it starts to get really clever. By combining just two of these different logic gates, an AND gate and an XOR gate, we can create a circuit that does something you're actually familiar with, basic math. It adds two bits together, and it can even carry the 1, just like you learned in elementary school. It's like we're building with digital Legos. And look, don't think this is just some small party trick. When you combine millions of these simple little adders, you get the processing power that's at the absolute heart of so many things you use every day. It's the arithmetic in your calculator, it's how your computer finds information in its memory, and it's even how we error check data that's flying across the internet. Okay, so our new digital brain can make decisions and do some basic math using just ones and zeros. That's great, but how do we represent more complex ideas, like, I don't know, the number 42? For that, we're going to need a formal language. Just think of it like this. We're all trying to say the same number, we're just using different languages. We humans, we use decimal, or base 10. Computers, with their on-off switches, they speak in binary, or base 2. And programmers? Well, they often use hexadecimal, or base 16, mostly because it's a really neat shorthand for those long, long strings of ones and zeros. Saying 00101010 is a mouthful, but 2A, that's much easier to work with. Have you ever seen a color code like this on a website before? That's hexadecimal in action. Each pair of characters there represents the amount of red, green, and blue light that you need to make that exact color. So hashtag FF5733 is really just a computer shorthand for a very specific shade of orange-red. It's a number that represents a concept from the real world. Pretty cool, right? All right, so we've got a language of numbers, but that leads us to the final and most crucial layer. How do we use these numbers to represent everything else? All the photos, the music, the text that makes up our digital lives. So the most basic way to store a number is with something called an unsigned integer. All the bits are used to represent how big the number is, so it's always going to be 0 or positive. And it's pretty simple. The more bits we decide to use, like 8 or 32 or 64, the bigger the number we can represent. So why does the number of bits actually matter so much? Well, take a look at this. A 32-bit system can use 32 bits to give a unique address to every byte of memory. That gives it a hard limit of about 4 gigabytes. But a 64-bit system? Whoa, it can address 16 times exabytes. Now that's not double, that is 4 billion times more. This is exactly why the jump from 32 to 64-bit computing was such a monumental leap forward for everyone. This brings up a really fascinating little problem. Think about it like an old-school car odometer. If your computer is using 8 bits, the highest number it can possibly count to is 255. So, what do you think happens when you try to add one more to that? What happens is the number overflows. It flips all the way back around to 0. And believe me, this isn't just some theoretical problem. As Alex, who's an embedded systems developer, points out, this is a very real-world issue. If his temperature sensor, which uses 8 bits, goes past 255 degrees, it could suddenly report 0 degrees, and that could cause a critical malfunction. So understanding these fundamental limits is absolutely vital. And that really gets to the heart of everything we've talked about today. It's such an empowering idea. The most complex software, the most brilliant artificial intelligence. At the end of the day, it all just comes back to billions of simple switches, working together through layers and layers of logic. If you can really grasp that, you can grasp anything in computing. So I'll just leave you with this one question to think about. The next time you pick up your phone or you sit down at your computer, think about that incredible journey from a single grain of sand to the transistors, to the logic gates and the numbers that make it all possible. How does that change your view of the incredible device that's right there in your hands? Thanks for joining me.